there was a cute problem in the book where there was a party going on and they needed to have enough tables to seat everybody. And they had these square tables and they wanted the tables to line up in a rectangle. And they wanted to know how many tables they needed to seat 22 people. I don't know if you remember reading about that problem in the book. So I'm going to use that problem to set up a pattern. And what I want to do is collect information about that by making a table about the tables. And we want to look at one, how many tables do we have? And two, how many people will be able to sit at the tables? So I'm going to have a summary table, but first I need some scratch work to kind of figure it out. So I got the grid here so I can draw on it. So my first table will sit 1, 2, 3, 4 people, right? One table, 4 people. So I'm just going to make a note in my side table, 1 table, 4 people. What happens if I put 2 tables together? Well, if I put 2 tables together into a rectangle, they're going to have to look like that. And we need people to have elbow room. And so we're going to do kind of a standard seating arrangement. There's going to be 1, 2 here at the top, 1, 2 down there at the bottom, and there's going to be 2 on each side. Right? Reasonable? So we have a party, we have 2 tables, we can sit 6 people. So I'm just going to make a note in my summary table. And anytime I'm trying to solve a problem, I'm always going to have scribbling and some way to consolidate that work, to neaten it up, try and find a pattern. And I'm not going to draw all the way up to 22 people. I'm just going to draw a couple of more stages of this. If I have 3 tables, then I'm going to have 3 people top and bottom and 1 person on each side. So that's 6 plus 2 is 8. And I'm starting to see a pattern develop. 1, 2, 3 tables, 4, 6, 8 people. In the picture, right? 1 table, there's 1 top and bottom, 1 on each side. 2 tables, 2 people top and bottom, 1 on each side. 3 tables, 3 people top and bottom, 1 on each side. I'm just going to jump down for fun. I'm going to skip 4, 5, 6, 7, 8. I'm just going to jump up. What if there were 10 tables? So I'm going to jump in my table all the way down to 10 and just think about it. Well, how many people will there be top and bottom based on the previous examples? 10 top and bottom. So I'm going to have 10 plus 10. And how many on each side? Every time it's 1 on each side. So then I'm going to have plus 1, plus 1, plus 1, plus 1. And that's going to give me 22 people can sit at 10 tables, right? Which was the answer to the question they had in the book. How many tables were needed for 10 people? So a couple of things going on here. There are 2 patterns happening here at the same time. One pattern is tables. That's a pretty straightforward pattern. 1 table, 2 tables, 3 tables, 4 tables. The first pattern here is we're just simply counting. 1, 2, 3, 4, and so on are referred to as the counting numbers. And anytime we're trying to find a pattern, there's almost always stages to it. And we're going to count those stages 1, 2, 3, 4. So finding patterns, one of our primary instruments to keep track of things is counting numbers to keep track. Even if you don't write the counting numbers down, you get a table and you have a first number in the table and a second number in the table and a third number in the table. They're there whether you write them in or not. So we need counting numbers to keep track. There's another pattern of numbers here, 4, 6, 8. I skipped over the next number. What would be after 8, do we think? 4, 6, 8. 10, and then 12, 10. And then we're going to keep going till we get to 22. Yeah, we're jumping by 2 there each time, right? So that's okay. You did an extra jump. That's all right. Yeah, so if I look at just like here, to get from 4 to 6, I would add 2. To get from 6 to 8, I would add 2. And so I just want to keep up that whole add 2 thing. And I want to do that over and over and over to continue this pattern. Okay. These kinds of patterns appear all the time around us. Sometimes they're really simple, like add 2, but they could be more complicated. Like, for example, check this next one out. 2, 4. Now, if I think about the previous pattern, the next number could be 6, but I'm going to pick a different number next. I'm going to put 8 next. If I put 8 next, anybody want to guess at what the fourth number might be? 16. Yeah, good.
16.
Excellent. Yep, you got it. 16. 2 winners. And then let's see, after 16, maybe 32.
32.
32 it is. Okay. And this is a different pattern than the one I had before. How would I tell somebody how to get the next number? Just times by 2. Yeah, instead of add 2 like we did before, this time we're doing a times 2. And so I'm just going to make a little note here. To get from here to here, I multiply by 2. Here to here, I multiply by 2. And so multiply by 2. Here to here, multiply by 2. And I didn't write my first number, second number, and third number like I did before, but these are in order, aren't they? Right. So I could say, I could make this into a table, but horizontal. And say, this is the first number, that's the second number, that's the third number, that's the fourth number, that's the fifth number. And if somebody said, can you give me the 100th number? Well, yeah, I could keep multiplying by 2 over and over again, but there might be a quicker way to get there. Sometimes there is, sometimes there isn't. This type of pattern here of doubling more generally is called a geometric sequence of numbers. So this is an example of a geometric sequence of numbers. Letter there, go. And geometric sequences appear in nature all the time. Like populations, we often wonder how much time does it take a population to double in size? Anybody ever have to take like something like ibuprofen for some ache or pain or bruise or bang? Right? Ibuprofen has what we call a half-life in the body. Every, I think it's 6 hours maybe, ibuprofen is half the potency in your body it was 6 hours before. Caffeine has a similar thing. Most people metabolize caffeine with a half-life of about 5 to 6 hours. So if you start with 100 milligrams in your body, 6 hours later is only going to be about 50 milligrams in your body. 6 hours after that, there's only going to be about 25. It's going to keep cutting in half. And these situations are called geometric sequences. Geometric sequences are where we have a repeated multiple, like always multiply by 2 or always multiply by half. Okay. So these are one of the common patterns we see in nature. Another pattern that comes up in a lot of places in nature, from reproduction to patterns on flowers to patterns in shells, is this pattern right here. So what I want to do is don't shout out any answers, but see if you can come up with the next 3 numbers in this sequence, in this list. A sequence is just a list, by the way. Write down that list and see if you can come up with the next 3 numbers in the list. Don't worry about being wrong. You're going to be wrong before you're right almost all the time. Katie or Christine or Jennifer online, if you ever want to type in an answer or shout it in, just go in there. Did you write something down?
Yeah.
Oh, good. Okay. What did you write down for the next number?
8.
8. 8 is the correct next number. Marcus, what you got?
13.
13. Someone else want to give us the flat third one there?
21.
21. Katie's got it too online. Thank you, Katie. Yeah, this set of numbers right here has a slightly different pattern than the previous 2. Instead of taking a fixed number like 2 and adding it all the time or multiplying by something, what it does is it just takes the previous 2 numbers, adds them up to get the next number. Okay, so wanted. Sum 2 consecutive terms to get the next. And I can totally describe like how to calculate a geometric sequence, right? I just double whatever number you're at, that's the next one, right? This is called a Fibonacci, this idea of summing the two terms to get the next one. Fibonacci. The first time it was publicized was a few hundred years ago in a math book where it was talking about reproducing bunnies. There's a story about it in the book. But the pattern 1, 1, 2, 3, 5, 8 comes up in a lot of other places. Like in flowers, this spiral seed pattern. There's one in the middle, one next to it, and then there's a chunk of 2, and then a chunk of 3, and then a chunk of 5, and then a chunk of 8 on average. Not perfect, close to that. And that's called a Fibonacci sequence. Is this the only Fibonacci sequence? No. You just pick any two numbers to start with and then use this procedure, and that's a new Fibonacci sequence. Okay. And they all have these pretty cool mathematical qualities to them that we could talk about for a day, but we have too many other patterns to talk about. Other patterns that we use a lot in our lives are like we talk about even numbers and odd numbers. So 2, 4, 6, 8. We just looked at that with that connecting the tables and how many people we can sit. 1, 3, 5, 7, 9, and so on. Even and odd are interesting because they both have something in common. How far apart are the numbers in pairs in both these lists? They're 2 apart. So if you said, I got a list of numbers and they're all 2 apart, can you tell me which list I'm talking about? No, it could be evens, could be odds, could be some in-between group. Anytime you have a list of numbers where they're always the same space apart, like these are +2, +2, +2, these are also +2, +2, +2. If they're equally spaced, like these are, they're called an arithmetic or arithmetic sequence. So equally spaced. All the time spelling as usual. And so in this next section, we're going to play around with geometric sequences and arithmetic sequences. And there's other sequences that are neither. Remember we were doing that introduction problem the other day? How many introductions do we need for 11 people or 7 people or so on? That is an interesting pattern of numbers. So let's see. At first, we get 2 introductions. And then there were 6 introductions. And then there were 12 introductions. And then there were, let's see, that's right, 20 introductions, 30 introductions, moving along. So this was for 2 people and 3 people, 4 people, 5 people, 6 people. Versus introductions, introductions. This doesn't fit the pattern where they're the same space apart, right? So if we look at how do you get from 2 to 4 with addition, or 2 to 6, you would add 4. From 6 to 12, you would add 6. From 12 to 20, you would add 8. From 20 to 30, you would add 10. So with an arithmetic sequence, it's got to be the same number in between. But here, the number in between is increasing as we move along. But I could do a second stage in this, right? How the green numbers are how far apart each? They're +2. So this is an arithmetic because it's got to be the first set of differences that's the same. If the second set of differences, it's a whole nother kind of pattern. I'll talk about that a little bit later. But sometimes there's not going to be a steady difference till you get to the third set of differences. Okay. And this technique of analyzing a sequence is called the method of finite differences. And you can use it to analyze some patterns, but not all. Like watch what happens if we try this on the doubling pattern. Differences. Let's try it one more time before we move on. With the doubling pattern, I had 2, then 4, then 8. Then 16, go up to 32 again, and it keeps going, doubling. If I use differences, in other words, what do I add? To get from 2 to 4, I would add 2, 4 to 8, I would add 4, 8 to 16, I would add 8, 16 to 32, I would add 16. What's the next row going to look like? To get from 2 to 4, I add 2. To get from 4 to 8, wait a minute, this is starting to look repetitive. Didn't we already do this? Is this giving me any new information? Nah. So in this case, the method of finite differences doesn't work. So it works on a lot of sequences, but sometimes it's just useless. Didn't work there. Instead, we have to notice, oh, double, multiply, don't add, multiply. Right? There's many kinds of patterns out there. There's many techniques for analyzing. Okay? We could spend all quarter just talking about different kinds of patterns. We're just going to spend 2 days on it. So patterns, super important in playing with numbers. Sometimes we can draw pictures of the patterns. They're called figurate numbers. So here's my first picture. Here's my second picture. Here's my third picture. Can you guess what the fourth picture is going to look like? Yeah. So what, tell me, describe the fourth picture to me. Sure.
It will look exactly like your blue picture.
Okay, like the blue one.
And 4 more dots
4 more dots where?
underneath.
Underneath. Okay, so if I put like 4 dots down and then I draw just like the blue picture above it. So all of these pictures have a triangular shape, well, except the first one, that's kind of lame. But if I count the number of dots, there's 1 dot and 3 dots, and then there's 6 dots, and then over here there's going to be 10 dots. And they form a sequence of numbers. Now check out that finite difference method on this sequence of numbers. To get from 1 to 3, I should add 2. From 3 to 6, I should add 3. And from 6 to 10, I should add 4. Right? Pretty straightforward. Is this what we call an arithmetic sequence? Is the number I add always the same? No, so it's not arithmetic, it's some other kind of sequence. But can't we continue it? Like if somebody said, okay, what's the 10th figure look like and how many dots there are? We could figure that out, couldn't we? We have to do some work to get there, but we have the pattern in front of us. Okay. So a lot of times in math, people think you need a formula. You don't necessarily need a formula, but you do need some kind of procedure. And in our heads right now, we have this idea about what this procedure is. And we can describe to somebody to draw the 10th figure, draw 10 dots. Above it, draw 9 dots. Above that, draw 8 dots. Keep going until you get to 1. If it looks like a triangle, you did a good job. Right? I might say that. What about the 100th one? Great. Start with 100, drop a dot each row. Get to 1 dot. You got it. Right? We can describe that to somebody. Okay? Even if we don't have a formula. But formulas are nice sometimes. We'll play with formulas next. Lost my mouse. One of those days. It's on my touchpad.